Urysohn embedding theorem. If X is a second-countable normal space, then there exists a homeomorphism f of X onto a subspace of R infinity, and X is therefore metrizable. In other words, X can be embedded as a topological copy inside the countable product of real lines. Key terms. A second-countable space has a countable basis for its topology. A normal space is one where disjoint closed sets can be separated by disjoint open sets. R infinity is the countable product of real lines, R cross R and so on, with the product topology, and it is metrizable. An embedding is a homeomorphism of X onto a subspace of another space. Metrizable means the topology comes from a metric. Strategy. Our plan is to build a single continuous map f from X into R infinity, using countably many continuous real functions as its coordinates. If this map is an embedding, injective, continuous, and a homeomorphism onto its image, then X is a topological copy of a subspace of the metrizable space R infinity. Hence X is metrizable. Step 1. Since X is second-countable, fix a countable basis B1, B2, B3, and so on. Consider all pairs of basis elements Bn and Bm such that the closure of Bn is contained in Bm. There are at most countably many such pairs. For each such pair, the closure of Bn and the complement of Bm are disjoint closed sets in the normal space X. Step 2. Apply Urysohn's lemma to each such pair. For every pair where closure of Bn sits inside Bm, Urysohn's lemma gives a continuous function fk from X into the closed interval 0 to 1, which is 0 on the closure of Bn and 1 outside Bm. This produces a countable family of continuous functions, f1, f2, f3, and so on. Step 3. This countable family separates points from closed sets. Take any point X and any closed set C not containing X. The complement of C is an open set containing X, so it contains a basis element Bm around X. By regularity, which follows from normality, there is a basis element Bn with X in Bn and closure of Bn inside Bm. The corresponding function fk is 0 at X and 1 on C. The family separates points from closed sets, and in particular separates distinct points. Step 4. Define the embedding map. Let f of X equal the sequence f1 of X, f2 of X, f3 of X, and so on. This maps X into R infinity, the countable product. Since each coordinate function fk is continuous, the map f is continuous into the product topology. Because the family separates distinct points, f is injective, different points have different images. Step 5. F is a homeomorphism onto its image. F is continuous and injective. To show it is an embedding, we check that F is open onto its image, that is, F carries open sets of X to open sets of F of X. This holds precisely because the family separates points from closed sets, each basis neighborhood of X is detected by some coordinate fk being small. Therefore F is a homeomorphism of X onto the subspace F of X inside R infinity. Conclusion. X is homeomorphic to a subspace of R infinity. Since R infinity is metrizable, every subspace of it is metrizable. Therefore X itself is metrizable. The Urysohn embedding theorem is proved, a second-countable normal space is always metrizable, and lives as a topological copy inside the countable product of real lines.